the chapter on X-ray diffraction. This is an additional chapter that we are looking into, something which is normally not taught at an undergrad level, but considering the frequency with which this technique is being used and the importance of the technique, I have decided to include this technique in this course. Uh, the first thing you need to understand is that just like we humans have our own distinctive identification in terms of our fingerprint pattern, every human being has its own distinctive identification as his fingerprints. Similarly, materials also have their distinctive identification that is based on the crystal structure, and X-ray diffraction is a technique that helps you identify that distinctive pattern. In other words, it helps you identify materials. So before we begin into uh, the details of how X-ray diffraction technique helps you identify the crystal structure of a material, or in other words, it helps you identify the materials, we would start with some basic concepts about the crystal structure, the microstructure, grains, their orientation, and the generation of X-rays and how X-rays interact with materials. So we'll begin with the understanding of materials in somewhat more detail in the initial half. Then we'll look into the characteristics of X-rays and how X-rays can lead to constructive or destructive interference. And once we understand that, we'll then look into the interaction of X-ray with materials and how that interaction could be used to uh, identify materials, the analysis part. So uh, before I move on towards X-ray, let us first look into the crystalline and non-crystalline materials. We need to understand them, and we need to understand what is meant by single crystals and polycrystalline materials and what is meant by anisotropy. All right. So let's say I have a container in which I have molten liquid or molten metal. What do you expect from the atoms in a molten state or a liquid state? What do you expect about their movements and their arrangement in a three-dimensional space?
So randomly moving.
Yes.
Sir,
So
container की shape में
randomly
arrange.
moving, diffused into one another.
the movement and arrangement would be random. Clear enough?
Yes, sir.
All right. Now, as soon as I begin the solidification process, that means I'm starting to convert this liquid into solid, atoms would start arranging themselves in an order. All right. I'll not go beyond that, but there would be a periodic arrangement that atoms would start falling into. We have looked into this atomic arrangement in terms of unit cells. Unit cells are the smallest uh, pattern in which atoms arrange themselves for a specific material, and that pattern essentially repeats in the three-dimensional space. So different materials would have different unit cells and different atomic arrangement. For example, FCC would have a center atom sitting at the center of each face of the unit cell, and that pattern would be repeating. Similarly, body-centered cubic crystal structure would have an atom at the center of the cube, and that pattern would essentially be repeating. So different materials would have different patterns. Now, if that arrangement is uniform, that means Although if I draw a unit cell over here, let's say body centered cubic arrangement, I have 8 corners and 8 atoms at the corners and one at the center. This arrangement would essentially remain the same. Atoms would be arranging themselves in this pattern, and this pattern would be repeating. But there is no compulsion on the orientation of this pattern. That means if I look at the face of a body centered one, if I'm looking from the front, there are 4 atoms sitting. So it is possible that atoms over here, they form this arrangement over here, and that arrangement continues in this direction. But there is a possibility that atoms at this lower right hand side, they have the same arrangement, but the orientation is different. The orientation in which they are arranging themselves is different from this arrangement. Is this point clear to you? Similarly, you could have a different arrangement over here. The spacing between atoms is the same since the material is same, and the way in which they are arranging themselves, it also is same, but it's just the orientation in which this arrangement is taking place is different. Are you getting the point?
यस यस सर, तो एक ही मटेरियल में बहुत सारी अरेंजमेंट्स हो सकती हैं.
It is not the arrangement which is different, it is the orientation of that arrangement which is different. You need to understand कि ओरिएंटेशन, जिस ओरिएंटेशन में वो अरेंजमेंट हो रही है वो डिफरेंट है. लेट्स से एक क्लास में ये बेंचेस पड़े हुए हैं, इस बेंच पे 2 स्टूडेंट्स यहाँ पे बैठते हैं, 2 यहाँ पे बैठते हैं, 2 यहाँ पे, 2 यहाँ पे, सिमिलरली सो ऑन एंड सो फोर्थ. ये अरेंजमेंट जो है ना एटम्स का, इफ आई टेक दिस स्मॉलेस्ट यूनिट, दिस अरेंजमेंट is the same throughout the class. Within this class, the orientation is also the same. लेकिन इसी क्लास में अगर कोई बेंच ऐसे पड़ा हुआ होगा जिसमें एटम्स की अरेंजमेंट, यूनिट सेल की अरेंजमेंट वही होगी, लेकिन इसकी ओरिएंटेशन इससे डिफरेंट होगी. दिस इज द नॉर्मल फॉर दिस ओरिएंटेशन एंड दिस इज द नॉर्मल फॉर दिस ओरिएंटेशन. सो इसेंशियली इन दोनों ओरिएंटेशंस के दरमियान कोई एंगुलर डिफरेंस है. So what you need to understand is that when atoms are solidifying, there is a possibility कि उन सब की ओरिएंटेशन एक ही हो, एंड देयर इज अ पॉसिबिलिटी कि उनकी ओरिएंटेशन एक दूसरे से डिफरेंट हो. डिफरेंट ग्रुप्स जो डिफरेंट लोकेशंस पे सॉलिडिफाई हो रहे हैं, उनकी अरेंजमेंट वही हो, लेकिन द ओरिएंटेशन एट विच दे आर अरेंजिंग माइट बी डिफरेंट. इज दिस पॉइंट क्लियर टू यू?
यस
Yes,
सर.
sir.
ऑलराइट. सो हम सिंगल क्रिस्टल्स किसको कहते हैं? वी रेफर टू सिंगल क्रिस्टल्स जिसमें when the solidification is taking place, the orientation remains same. There's only one orientation in which solidification is taking place. If atoms are solidifying themselves, they are solidifying themselves in a single orientation. ये एक orientation है, इसके अंदर solidification हो रही है. Alright? It says for a crystalline solid, स्ट्रक्चर किसका होता है? क्रिस्टलाइन सॉलिड का होता है. देयर इज पीरियोडिक एंड रिपीटेड अरेंजमेंट ऑफ एटम्स इन परफेक्ट ऑर्डर which extends throughout the entity of the specimen without interruption, and that results in single crystal. Interruption क्या होती है? I'll come to that when we'll discuss polycrystalline materials. All unit cells interlock in the same way and have same orientation. This is for single crystals. Now, single crystals exist in nature, but they may also be produced artificially. The problem is they are difficult to grow. एक क्लास में बहुत से स्टूडेंट randomly distributed हैं as until the teacher hasn't come. The moment teacher has come, you start sitting on your benches. All right. बट इन ऑर्डर टू कंट्रोल यू कि आप एक परफेक्ट ऑर्डर में एक परफेक्ट ओरिएंटेशन में बैठें कि पहला स्टूडेंट इधर आके बैठे फिर उसके बाद स्टूडेंट इधर आए फिर 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 बजाय इसके कि एक बेंच इधर करके स्टूडेंट इस तरह बैठना शुरू कर दें. इट इज़ डिफिकल्ट टू कंट्रोल द ग्रोथ or solidification process in order to control the orientation or in order to maintain a single orientation. Where you have to control this, you have to strictly control the environment or carefully control the environment. All right. So single crystals which have a single orientation, they are difficult to grow environment and you have to control the environment. Is this point clear to you guys?
सर आपकी आवाज काटती है
जी
सर आपकी आवाज एकदम कटती है सर, लास्ट फिक्र अपना रिपीट कर दें.
All right, just give me a minute, let me change the internet connection first. All right, can you guys hear me?
यस सर
Yes, sir.
Time?
Yes, sir.
Time. Can you turn off your mic, turn off your video, please? Mohammad Saim Kamar. Beta, I am not interested in what you are doing at your home, so kindly turn off your videos, please.
सर सारे स्टूडेंट्स.
All right.
Sir,
The slides are visible to you guys?
यस सर.
Yes, sir.
All right. Is my voice clearer or not?
Yes, sir.
नाउ क्लियर
All right, great. So what I was trying to say is that you know the difference between single crystal and polycrystalline material now or not?
यस सर.
सर आप
क्लियर हो
लास्ट
गया.
सेंटेंस बोला था वो रिपीट कर दीजिए वो जो अब आपकी डिस्ट्रक्शन आ गई
All
थी
right.
थोड़ी सी.
So as long as single crystal and polycrystalline materials, the concept is clear to you guys or not?
Yes, sir. Clear है.
All right. Now, all right. If the concept is clear, what I was trying to say in the last part was that single crystals are ordinarily difficult to grow because you have to control the environment in order to maintain a single orientation. Clear enough?
सर एक क्वेश्चन मेरा.
जी
सर ये बुक में लिखा हुआ है इनफाइनाइट पीरियोडिसिटी, इसका क्या मतलब है कि इनमें इनफाइनाइट पीरियोडिसिटी होती
it that means that the periodic order is for a very long range.
है? ठीक है सर.
All right.
यस सर. ओके.
All right. Moving on to polycrystalline materials. Most crystalline solids are composed of a collection of many small crystals or grains. So you know a single crystal that it has one orientation. When you say polycrystalline material, you have many crystals having different orientations. So this is crystal 1 having this orientation, there is another crystal having this orientation. So it is polycrystalline material is a material which has many single crystals in it. Clear?
यस सर. क्लियर.
यस सर
So during the solidification of polycrystalline specimen, initially small crystals or nuclei form at various positions. So that means when you are solidifying within this container, there would be a group of atoms that would have one orientation. There would be another group of atoms that would have another orientation, another group, another orientation. So there would be many small crystals that would start to grow with regards to their own individual orientations. These crystals would have random crystallographic orientations. That means they'll grow at random crystallographic directions. The small grain grows by successive additions from the surrounding liquid of atoms to the structure of each. So that means that if few atoms are growing in this orientation and this is their orientation, there would be atoms coming in from the liquid and joining in this orientation. Similarly, if atoms are growing in this orientation, there would be atoms coming from the liquid and joining this orientation. So they'll grow up upon the liquid by consuming the liquid and converting into solid. The extremities of adjacent grains impinge on one another as the solidification process approaches completion. Let me come to this point in a minute's time. The crystallographic orientation varies from grain to grain. Grain and crystal, they are one and the same thing. Also, there exists some atomic mismatch within the region where two grain comes in contact. This is called grain boundary. So, what is grain boundary? We'll look into it next slide in the next slide, and it will become clearer to you. This is the image of a material under microscope, optical microscope. I'll tell you what the regions are. Region within a boundary. This white region is one grain or crystal. And this blue region is the grain boundary. So let us look at this region and try to understand what is happening in this region. In this region, what happened was initially atoms started coming together in this orientation. यहाँ पे atoms arrange होना शुरू हुए और they started growing in this direction. So this is the direction or orientation 1 for grain 1. The atomic distance remains the same. It is just the way in which atoms are growing from liquid to solid. This is orientation 1. Similarly, within the same liquid, there were certain atoms that started growing in this orientation. So they started growing as another orientation, which is known as orientation 2. Then there was another set of atoms that started growing in this orientation, which is orientation 3. Now, the crystal structure is the same. The atomic distance between atoms is the same. For example, you are looking at the front face of an FCC. So atoms, they are arranged in this manner and the distance between atoms is the same for all the three grains. But it's just the way they are growing is different. Now, what would happen when these two orientations or these two orientations or these two orientations, these orientations come in contact? When these orientations come in contact, essentially it would be very difficult whether they should follow orientation 1, orientation 3 or orientation 2, since they have to select one of the orientation in order to grow. Essentially, there would not be any atomic arrangement within this region, and this region is essentially would have loosely held atoms, and the region is known as the grain boundary, which is a highly energetic area. Atoms are at high energy within this area. This would be your grain 2 or crystal 2. This would be your crystal 3. This would be your crystal 1. So grain or crystal, they are interchangeable terms. Where the grains come in contact with each other, they'll form a region of loosely held atoms, which is known as grain boundary. And atoms at grain boundaries, they are highly energetic. Clear enough?
सर ये फिर इसकी एटम की यानी कि ये सॉलिड की स्टेबिलिटी को इफेक्ट नहीं करेगा जब एक जगह पर उसका यानी कि उसकी एनर्जी ज्यादा और दूसरी जगह पे कम है?
करता है स्टेबिलिटी ग्रेन बाउंड्री एज सच नहीं करती. ये जो आप लाइंस देख रहे हैं, ये लाइंस अपीयर ही इस वजह से होती हैं कि आप मटेरियल को किसी केमिकल से रिएक्ट करवाते हैं और चूंकि ये एटम्स दे आर हाईली एनर्जेटिक, तो ये रिएक्ट कर जाते हैं और यहाँ पे से मटेरियल गायब हो जाता है. सो दैट्स व्हाई व्हेन यू सी इट अंडर लाइट, दिस ग्रेन बाउंड्री अपीयर्स टू बी डार्क, बिकॉज जब इस पर लाइट पड़ती है तो लाइट इज नॉट एबल टू कम बैक आउट ऑफ this area where material has been removed. लेकिन जो white area है, चूंकि वहाँ पे still material मौजूद होता है, तो it is able to reflect the light. So you are able to see the contrast between the grain and grain boundaries due to this reason. atoms are highly energetic, highly reactive in the grain boundary region. Clear enough? लेकिन सारा material reactive नहीं होता क्योंकि there is still 95% of the material which is again very in a very stable form.
Clear.
Is the point clear?
Yes, clear.
All right. So from the point of view of X-ray diffraction, you need to understand that a polycrystalline materials would have different orientations, and orientation is just a direction. So be careful or be mindful of the word orientation or direction within a polycrystalline material. एक्सरे डिफ्रैक्शन आपको ये भी बताता है कि किस ओरिएंटेशन या किस डायरेक्शन में ग्रोथ ज्यादा हुई है. ऑलराइट, we'll come to know of that later on, but just to have an understanding of what is a polycrystalline material, what is a grain, what is a grain boundary, and how do you differentiate different grains. I hope this point is clear to you guys.
Yes, sir.
All right.
Yes,
great.
sir.
Great. Again, I have emphasized over here that each grain is a single crystal because it's having its own orientation. So single crystal, how many grains are there in a single crystal?
Infinite.
Sir, infinite.
How many grains are there in a single crystal? जी?
सर वो एक
सर आपने नीचे लिखा है each grain is a single crystal, तो एक
Sir,
grain
each
एक
grain-
single crystal के अंदर
एक ही होगा सर.
एक ही grain होगा. Very good. So that's why you differentiate materials as single crystal or polycrystalline materials. Polycrystalline materials would have multiple grains in them. Right. So now once we have looked into the microstructure of a material, let us try to understand what is the information we can get out of X-ray diffraction. X-ray diffraction, as it says, is a non-destructive technique. It's a technique that, can you guys hear me?
जी सर आवाज आ रही है.
Yes, sir.
Right. It's a non-destructive technique. That means it's a technique where material is not destroyed. All right. You can use the material once the test has been performed. So X-ray diffraction is a non-destructive technique widely used for characterization of crystalline materials. The method has been used for the determination of crystal structures. Since we have studied body-centered cubic and face-centered cubic structures, so I'll keep my discussion up to these two structures. Simple cubic means only 8 atoms, each placed at the corner of the cube. There is no other atom other than that at the corner of the cube. So simple cubic structure is just the basic structure for body-centered cubic or face-centered cubic. So the method has been used for the determination of crystal structures. It is used for the determination of lattice parameter, interplanar spacing. What is interplanar spacing? We'll come to know of it. And atomic radii. This atomic radii would essentially give me the information of about the material if it is in the elemental form. But before that, can different materials have body-centered cubic crystal structure?
Yes,
क्या
sir.
मतलब सर सवाल क्या
Yes,
पूछा
sir.
आपने?
Can different materials, let's say aluminum and copper, could they have face-centered cubic crystal structure? Is it possible?
Yes, sir.
So what would be the difference between, how would you differentiate between aluminum and copper if they have FCC structure?
सर उनकी वैल्यूज से सर कोऑर्डिनेशन नंबर वगैरह.
सर हम इनकी
Coordination.
डेंसिटी फाइंड कर सकते हैं क्या, या फिर उसकी कोई भी एटॉमिक पैकिंग फैक्टर किसी तरीके से?
डेंसिटी भी इनकी डिफरेंट होगी सर.
आप इस स्ट्रक्चर की फॉर्म में देखें और मुझे ये बताएं कि लेट्स से आई हैव दिस FCC structure.
सर उनके रेडियाई डिफरेंट होंगे तो लेटेस्ट पैरामीटर डिफरेंट होंगे.
Very good. Very good. The difference would be in their
अच्छा दूसरा इशू जिसके
lattice.
मैंने लिखा है कि ब्रांच के
Alright.
बाहर बहुत ज्यादा या ब्रांच के अंदर बहुत ज्यादा चोकिंग तो नहीं है ना, सारे प्रोटोकॉल्स ऑब्जर्व हो रहे हैं.
Beta, could you turn off your mic, please? All right. So the structure would essentially be the same, but the difference would be in terms of lattice parameter. That means the dimensions of the cube, and that would be due to the atomic radii of the material. Is it clear?
Yes sir.
जी सर.
In other words, if you identify the structure as FCC, that is not sufficient enough for you to identify the material. It is the lattice parameter or the atomic radii. For elemental form, it is atomic radii. If you have a compound or a molecular structure, it is basically the lattice parameter that would help you identify the crystal structure, identify the material. Clear?
Yes sir.
Beta, could you turn off your mic, please? All right. So now this is the information we can get out of X-ray diffraction. How we get out of it with using X-ray diffraction, we'll look into it. But before that, how the X-rays are being generated. X-rays are usually produced by bombarding a metal surface with high energy electrons traveling along an evacuated space or pathway. On the impact of these electrons, they exchange momentum with the electrons of the metal, including the inertial electrons. And what happens is that these high energy electrons, they once come in contact with the inertial electron of metals, the inertial electrons of the metal are removed, and they are being replaced by the electron from a higher level energy shell. As an electron jumps from higher energy level to a lower energy level, the difference in energy is released in the form of radiation, which corresponds to the X-ray generation. Clear?
Yes.
All right. So in X-ray diffraction machines, you usually used a tungsten filament. This tungsten filament is provided with a very high voltage, and once the voltage exceeds the work potential of this filament, electrons start ejecting out of this filament. And there is a high potential difference that is being maintained between the filament and the target metal, which normally in X-ray machines is a copper metal. As a result of this, electron comes and interact with the inertial electrons of copper metal, removing them from the inner shells. Outer shell electrons jump into the inner shell, and the difference in the energy is basically released in the form of X-rays. So this is how X-rays are being generated. Clear?
Yes sir.
All right. Now, before we begin understanding what is interplanar distance, how the crystal structure is being deciphered, you need to understand that X-rays, when they interact with material, they result in the phenomena of diffraction or scattering. And this diffraction occurs when an X-ray encounters a series of regularly spaced opticals. What is this series of regularly spaced opticals? X-rays मटेरियल से निकल के जब कॉपर सोर्स से निकल के जब मटेरियल के साथ इंटरेक्ट करती हैं तो उनको ऑब्स्टिकल्स मिलते हैं जो कि रेगुलरली स्पेस्ड होते हैं. व्हाट इज दिस रेगुलरली स्पेस्ड ऑप्टिकल्स?
सर वही यूनिट सेल्स नहीं है
Pins or
Crystal.
unit cell.
जी जी.
It is basically the atoms. All right.
Yes
It
sir.
is basically the atomic arrangement. The important condition for X-ray diffraction is that the spacing between the atoms, it should be comparable in magnitude to the wavelength of X-ray. So X-ray wavelength and the atomic distance, the distance between the two atoms. This should be the lambda of the X-ray, and the atomic distance, it should be comparable in size. As I have mentioned, copper source is being used, or copper target is being used. So X-rays that are being generated are basically copper X-rays or copper source X-rays that have a fixed lambda. The lambda is fixed in X-ray diffraction experiment since you are using copper source, a fixed source. Furthermore, diffraction is a consequence of specific phase relationship between two or more waves that has been scattered by these obstacles. So what are the phase relationships that can essentially take place in an X-ray diffraction experiment? Let's look into that. One of the phenomena is constructive interference. Let's see what the constructive interference means. You have two waves, X-ray waves, wave 1 and wave 2, having lambda as the wavelength and A as the amplitude. When these waves come and interact with the material having specific periodic arrangement, or there is a series of obstacles that are there could be two events that could take place, two extreme events that could take place. One of the event is that after the scattering or after interacting with the material, the wavelength remains in phase. Amplitude doesn't get affected, but the wavelength or the waves, they basically remain in phase. When these two in phase waves come and join together, amplitude gets multiplied. All right. This is the phenomenon of constructive interference. This constructive interference would only take place when after the scattering event, the path length difference is essentially an integral number of wavelength. If the path length difference is integral number of lambda, you would essentially have constructive interference. Is this clear to you guys?
सर ये
पाथ
तो वो मेरे ख्याल सुपर
जी
पोजीशन
सॉरी
प्रिंसिपल यूज हो रहा है यहाँ पे
सॉरी
सर यहाँ पे सुपर पोजीशन प्रिंसिपल यूज हो रहा है ना
जी सुपर इम्पोजिशन यूज हो रहा है, लेकिन उसके लिए शर्त क्या है? उसके लिए शर्त यह है कि आफ्टर दिस स्कैटरिंग इवेंट और आफ्टर इंटरैक्टिंग विद द मटेरियल, द waves should remain in phase such that the path difference between the waves should be either lambda, 1 lambda, 2 lambda, 3 lambda, 4 lambda. It should be an integral multiple of lambda. Clear enough?
सर इसके
Yes, sir.
रीजन क्या होगी?
जी
सर इसकी रीजन क्या होगी कि वो इंटीग्रल मल्टीपल लैम्डा का होगा?
इसकी रीजन क्या होगी, क्या मतलब?
सर इस बात की समझ नहीं आई, आपने जो कहा ना कि वो इंटीग्रल मल्टीपल होगा लैम्डा का। पाथ
आप
लेंथ
फिलहाल सिर्फ आप फिलहाल सिर्फ ये समझें, आई एम टेकिंग यू स्टेप बाय स्टेप. सो फिलहाल you need to understand that there would be constructive interference if the two waves, the difference in their path is essentially lambda or multiple of lambda. ये बात क्लियर है या नहीं है?
यस सर ये क्लियर है।
बस just hold on to this thought at the moment. Why is it 1 lambda or 2 lambda or 3 lambda? We'll come to know of it once we look into the interaction. Clear?
यस सर क्लियर है।
All right. Now, this is one of the possibilities. Another possibility is that you have similar two waves. This is wave 1 and this is wave 2. And once these two waves having the wavelength of lambda and amplitude of A, they come against any scattering event, there is a path difference of lambda by 2. हाफ लैम्डा. ऑलराइट, अगर आप ये देखें तो इन दोनों के दरमियान जो डिफरेंस है दैट इज एसेंशियली ऑफ लैम्डा बाय 2. क्लियर?
यस सर।
Case you would have a destructive interference and the amplitude would essentially cancel out each other. So amplitude basically reduce हो जाएगा if you have the scattering event in terms of half lambda. I mean, the path difference becomes a multiple of half lambda. Clear?
Yes, sir.
Yes. Right. Now, once you have understood the phenomena of constructive interference and destructive interference, let us try to understand what is interplanar distance or distances, which is represented by DHKL. We'll try to understand what is DHKL. It's almost 9:30. Let's have a break and then we will come back and we'll try to understand what is meant by the path, the interplanar distances. All right.